everybody, and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors. This is lecture number 40, and we will start with the fabrication of FinFETs, maybe a couple of slides, and then we will see a brief modeling of FinFET, how we model a device, and then we will finish with the high frequency modeling, right. High frequency means when the frequencies are above gigahertz value. The knowledge base which is required here is maybe a brief idea. I would recommend that you study brief idea about Y parameter. What is the meaning of Y parameter? How Y parameters are calculated in electrical courses. So if I have a two-port network, how do I calculate Y parameters? That knowledge base will help you to grab understanding of this lecture, and a slight basic idea about the capacitance model of a FinFET, which though I will be actually dealing with that during the course of the time. So let me come with the FinFET fabrication process steps. So we go from left to right of your screen, and look at the first one. You have this substrate here. The blue colored silicon substrate is there, over which we have a hard mask. The brown colored one basically is the hard mask, which you do so that the substrate does not get oxidized beyond a particular point. This is step number A, which you do. Then what you do, you etch the fin. Etching the fin basically means that using an etchant, you try to remove the silicon in a manner shown here, right. Though there are many intermediate steps in between, I am keeping it to the basic bare minimum. Maybe a course on fabrication will help you to understand the each and every part of this discussion. I will keep it to very bare basic and explain to you, keeping the hard mask as it is, right. And then you do an oxide deposition. For example, you do a silicon dioxide deposition. So what does the oxide does is that it passivates the surface. At these places it passivates the surface, at these places and at these places it passivates, which means that it does not allow for any further oxide growth there. After that, this is done, which is basically the planarization process, which means you plane it up using a mechanized planer, and you try to make it as plain as possible, right. This is known as patterning, silicon fin patterning. This is known as patterning. Okay, yes, this is written here. It is patterning is there. Silicon nitride is used as a hard mask, and silicon dioxide cap is used to relieve the stress. So typically what happens is that if you have certain layers, you basically do what in fabrication process steps is that you heat up and then anneal. When you heat up and anneal, the expansion rates of two different materials are different, and as a result what will happen is that the interface where the two materials meet, you will have a typical stress being developed, right. These stress are not good in a sense, because from device fabrication point of view, because they will tend to have larger therefore traps and so on and so forth, which is not expected to happen for an actual device. So therefore you generally use a silicon dioxide cap layer to relieve this stress. So silicon has a better interface property as compared to anything else, and then we grow a thin silicon dioxide sacrificial layer, as you can see. So we have finished with the last one here. So just keep in your mind this last figure where the oxidation has been done here, here, and at this particular point. Now after you have done that, then you etch away the oxide layer, right. So we have initially etched away the silicon layer, and now you etch away the oxide layer. When you etch away the oxide layer, this is known as a recess etch, right. And the sacrificial oxide layer, which was initially available here, here, and here, is completely removed to remove any etch damage. So when you put an etchant, not only destroys the oxide layer, it also tries to destroy the nearby layers. So when you therefore remove the oxide layer from that particular point, you end up having almost sort of trap free design available with you. After this step, if you see this red colored oxide, this red colored is a thin oxide which you grow, right. This is the MOS oxide which you grow. This is also referred to as a gate oxide or a MOS oxide, right. and this gate oxide is the red colored which you grow, and this goes over the hard mask over the silicon dioxide and so on and so forth. And then finally you do a metallization layer where the green colored is basically the metal layer which you do, metal. This is the metal layer. So you have one fin here, fin 1, and this is fin 2. So there are two fins which are available located side by side, and this is the fin pitch. The distance between them is the fin pitch which you see, right. And then you can use a metal layer, or you can use a polysilicon gate for that matter, right. And this is quite helpful in designing. So this is the basic fabrication steps. I am not going into details of it. You can find it in many of the other details as such. Now let me explain to you two types of, there are other structures also, but I will be focusing on two types of basic structure of FinFET, right, based on how the gate is surrounding the channel and how the potentials or the biases are given to the gate. So if you look at the left FinFET, which is basically the shorted gate FinFET, so we refer to this as a SG FinFET, and on the right hand side we have an insulated gate FinFET, right. So on the left hand side you have a shorted gate FinFET, on the right hand side you have an insulated gate FinFET. The shorted gate FinFET means that any potential you give on the gate, right, is applicable to all the three gates. So if you give a potential here, let us suppose VGS, then that appears here, here as well as here. So all the three sides of the channel will have the same potential, and the channel will see the same potential provided the oxide thickness is same in all the three directions. I will refer to this more in details now. However, if you look on the right hand side, I can give individual potential to gate 1 and to gate 2. This is known as an insulated gate FinFET, right. This is known as an insulated gate FinFET. So I have a shorted gate FinFET and I have an insulated gate FinFET. The advantage and disadvantage both will have it. So as you can see here, a shorted gate will have 3 terminals, source, drain and one for gate, but insulated gate will have source, drain, and it will have one terminal for gate 1, another for gate 2. Typically they have a higher I on and I off current, and threshold voltage modulation is possible here by using a backgate. So this basically looks like a double gate structure, double gate non-planar structure, right. Why double gate? Because on the both sides you have one gate and another gate, and non-planar because it is a 3-dimensional plane, it is extended. So therefore it requires more area. So double gate means you have 2 gates on the both sides of a more area is required, less area. So the typical advantage of a single gate is lower area, it is higher on current but also higher off current. It is a 3-terminal device. Insulated gate will have 4-terminal device due to two gates. Threshold voltage modulation is possible using the second gate as the back gate, and more area will be required. What I was talking about earlier was that if this oxide layer, right, is very thick, the top oxide layer is very thick, then even if you apply the same gate voltage to the top gate and the side gates here, the effective voltage seen by the channel will be different from this side and this side. I will give you an example. Let us say I give here 1 volt, 1 volt and 1 volt. Oxide drop thickness here is 0.5. So the effective voltage seen in the channel will be 0.5 volts, on the back side also 0.5 volts, but since the top gate T oxide is very large, here you will actually see maybe a voltage of approximately 0.3 volts. So you see, by doing the oxide growth asymmetric across the 3 design, I can have the different values of voltages available to me at these 3 edges, correct, and therefore the threshold voltage will change. If you keep T oxide same in all the 3 directions, then obviously you will never have this problem. This problem will be solved in a sense that exactly the same potential will be visible to all of them. This I have already talked through, so I will quickly go through it already, that we have bulk FinFET on the left hand side, and we have a SOI FinFET on the left hand side, and we have a SOI on the right hand side and a bulk FinFET on the left hand side. So if you see, the only difference between these two is that I have a silicon dioxide layer in between the gate and the silicon substrate. So fin is over silicon dioxide, whereas in this case the fin is over the silicon substrate. This silicon dioxide is sort of an insulator which supports the gate. As I discussed with you, the height of the fin is relatively larger in case of bulk FinFET as compared to SOI FinFET. Bulk FinFETs obviously has some advantages, that is low cost, it is low defect density, there is no floating body effect unlike in SOI, right, and it is almost the same as your conventional bulk CMOS technology in terms of process flow. Whereas in the SOI, the major advantage, it suppresses the leakage current, and the reason is, since you have this thick silicon dioxide layer here, right, this does not allow for the back channel or the back gate reverse leakage current or the leakage current to flow, and it has got a relatively higher speed. However, there is a big problem with FinFET, with current SOI FinFETs. With current reduction in the technology and increase in the current and more density of these active devices within the chip area, your heat dissipation has to be also better, but that is not good for SOI FinFETs. And the reason is that since the silicon dioxide is a bad insulator of any heat, this is the active, this yellow one is the active area of the device, right, which active area means which wherein the current flows, and therefore the heating takes place in this active area only, right. So you have a large heating which is happening here. So if you are not able to disseminate this heat very easily, you will have self-heating effects coming into picture, and there will be large amount of degrading phenomena happening in the FinFET. That is the problem of a SOI FinFET, right. So typically for space application, many people use SOI FinFET, right. For bulk FinFETs, we use it for memory applications and so on and so forth. This we have already discussed, that there are two ways of looking at it, that my gate is a raised gate. So my gate is relatively, you see, it is much larger, it raised larger as compared to source and drain, and therefore the top gate thickness is much larger as compared to sidewall side thicknesses. The first thing is H fin is much larger than T fin. T fin is the thickness of the fin, right. This is the thickness of the fin. So this is your H fin, this one, right, wherein you are getting, this is your height of the fin, and this is your T fin. T fin is this one. So what I am assuming is my H fin is much larger than T fin, which basically means that the length height is larger. We have already discussed that the effective width will be given as T fin plus 2 times H fin, and the total L effective will be L gate. L gate is this gate plus 2 times the extension region. This is the extension region. This distance between the gate and the drain and the gate and the source is basically referred to as extension, right. And you can actually insert quite a different type of materials here known as spacer materials in order to improve the design characteristics or electrical output characteristics of the device, and this gives you quite a decent input output characteristics of the device. Let us look at so this is where we enter into the region of modeling of the device. So we have understood how a FinFET, so it is almost like a bulk device, it works like that only. The physics behind is exactly the same. Quantum confinement will come when the width of the fin is very small, lesser than approximately 5 nanometer. Advantages and disadvantages of bulk and SOI we have already discussed in this case. Now let us plot on the left hand side threshold voltage versus fin height, right. So what I am doing is I am increasing the fin height from a low value to relatively a larger value, and as you can see the threshold voltage actually goes on increasing, the mod value of it goes on increasing. The effective channel length is taken to be 60 nanometer. So what is effective channel length? It is L gate plus 2 times the L extension. So you can have 20 nanometer, let us suppose, equals to L gate, and maybe L extension to be equals to 20. So 20 plus 2 into 20, and that happens to be 60 nanometer. So L effective equals to 20. This is known as a symmetric design, because the distance from the gate to the source and gate to the drain is exactly the same. You can have an asymmetric design as well, which means that you can have the L extension towards the source end to be just 10 nanometers, and on the drain end it could be 30 nanometers. But typically we try to keep it symmetrical in nature. There are advantages of asymmetric design as well. However, let us concentrate on this figure on the left hand side. As you can see here, if your So this is your height of the fin. So one thing is clear, that as the height of the fin increases, irrespective of value of the thickness of the fin, the threshold voltage goes on increasing, and that's perfectly correct also, because as the height goes on increasing, you require a larger amount of charge per unit, or you require a larger total charge in order to form a channel, and that's the reason you require a larger gate voltage, and threshold voltage becomes larger and larger. And that's the reason you see that as you increase from 20 to 40 to 60 to 80, for example in 40 it is approximately minus 0.4 volts, whereas for 80 it is minus 0.6 for H fin equals to 60 nanometers. That is one observation. And the second observation is, as the value of your thickness of the fin material goes on increasing, the threshold voltage increases. That is also perfectly fine, because when you go on increasing thickness, your electric field reduces, and therefore electric field where? Electric field in the transverse direction, in the longitudinal, this direction. So basically I am increasing this T fin, this one, I am increasing this, and as a result what will happen is you require a larger gate voltage in order to form the channel there, and that is the reason threshold voltage will go on increasing as you move from a lower value of T fin to a higher value of T fin, right. That is what is being shown on the left hand side in this case. Let us look at the right hand side figure, and that tells me the x axis we plot SEP threshold swing, which is millivolt per decade. As I discussed with you, millivolt per decade, why? Because for a 1 decade change in the drain current, how much amount of gate voltage should I change, that is basically defined as my subthreshold swing, and therefore it is given as millivolt per decade. And if you plot that with fin height, then as the fin height increases, subthreshold swing degrades actually, which means that for a higher fin you require to give a larger SS subthreshold swing, or you require to give a larger gate voltage to do it. I will show you an example. Let us take 60, right, and let us take 80, or maybe it is easier to explain to you. Maybe take 60 and let us take 80 here. If you see the difference, you will see that, okay, I will make it more easier for you to this thing. Let us take maybe 20. So 20 is here, and let us take 80 somewhere here, right. So if you plot this thing, this is 90. So at 20 nanometer H fin, your SS is approximately 90 millivolts per decade. At 80 nanometer FinFETs, the SS is approximately 145, which means that you have to give 145 millivolts peak to peak swing in order to have a 1 decade change in the current, and that is true when your H fin has actually gone high from 20 nanometer to 80 nanometer. Try to think about it, why is it like that, which means the device is actually degraded with a higher fin. Similarly, if you increase the fin height or the fin thickness for the same value of H fin, you will get a larger value of your subthreshold swing, and that is what is important. The third important point which I wanted to raise out is, if you look at the left hand side, there seems to be a saturation tendency somewhere around here, right, which means for a higher fin the threshold voltage roll off does not take place infinitely large. It goes down and then sort of saturates beyond a particular value of H fin, and that is what I have written here, that is basically threshold voltage roll off, and similarly with that also H fin is increased. So when both H fin is increased, height of the fin is increased, there is both the saturation of threshold voltage as well as of the subthreshold swing. And now the critical height of the fin needed for saturation is dependent on T fin. That is quite an interesting phenomena. That means if my T fin changes, then the minimum height required to form the channel is also changing. Now if I have a larger T fin, the critical H fin for forming the channel is also higher, right. Just think about it, why is it like that? From primarily basic principles you will be able to generate this idea, why is it like this, that for lower high values of, means both increase in the proportionate manner. Let us look now at the threshold voltage versus fin thickness. So that was before with H fin, and now this is with T fin, right. And as you can see, as expected, as the T fin increases, I would expect to see the increment in the value of your threshold voltage. And if you look at the subthreshold swing versus T-fin, again the same phenomena, it goes on increasing, right. However, quite interesting phenomena which you should be aware of is, unlike in HFIN, there is currently, we do not see a saturation tendency, it rolls off more rapidly. So, the rolling off is more rapid in case of threshold voltage, and the rise is also very rapid in case of subthreshold swing. So, the subthreshold swing rise for a higher T-fin is much larger, right. So, if your HFIN is say 90 nanometer, then this rise is much larger as compared to this rise, which means that lower HFIN will entail a lower degrading effect of subthreshold for a varying value of T-fin. And this calculation was done with effective thickness of 60 nanometer, drain to source voltage of 1.5 nanometer. So, we have taken this from this reference paper. You can actually go through this reference paper. It is quite an old reference paper, but gives you a basic idea about the modeling techniques which are there. Now, so as I told you, fin thickness can therefore reduce the short channel effects. Now, as you can see here, if you both look at left hand side figure and right hand side figure, then as you make your HFIN higher and higher, the separation between the two goes on reducing, between two threshold voltage goes on reducing, which means that higher fin height or a larger fin thickness, right, in both the cases the variability is reduced drastically for the fin output, right, and that is two important takeaway from this slide as far as this discussion is concerned. Let me now come to some other. You already know that most of the FinFETs are square fin, like it goes like this. So, it is a square fin which we are talking about, right, but there are many others also, such for example, this is a non-rectangular fin which you get. Similarly, you can do the source drain region, you can reduce the doping very low, so that the resistance there actually increases, right. Then you can also do a dielectric thickness scaling, which means that the oxide thickness you can actually lower it down or make it high depending upon what is the requirement for your condition. For example, if you want that the device should work at very high speeds with lower cap, keep the oxide capacitance small because your on currents will be relatively large. If you want that the FinFET should work as a memory device, keep your oxide thickness relatively large and you can still get it, right. And you can do threshold voltage control using channel doping and using aluminum or various types of gates, right, that will result in the change in the work function of the material. And as a result, when the work function changes, you will have the difference in the electrical characteristics will occur in that case, right. So, this is what we get as far as a non-rectangular film is concerned, and then we do a source drain doping in series. One point which you need to also look into is, maybe I will show, yes, maybe I will just remove this. Let me use, okay, I do not know, I can use this slide, but let me use this slide, yes, and let us show to you that what is. So, if I have a FinFET structure, right, and I have this gate here, right, the 3-dimensional plane, and then if so, this is the extension region, right. So, you suppose your source drain starts from here, this is your extension region, and your source starts from this extension region. What you can do is you can actually do an oxide growth here, maybe you can do an HFO2, hafnium oxide, or even titanium oxide spacers, right. You can do spacers. When you put a spacer in middle, what you effectively do is that you actually tend to make electric fields converge very easily onto the channel and thereby reducing the threshold voltage. So, there is a cost you pay for it, is that you have an increased value of the capacitances, and that is the problem. So, that is what I was coming to in the next slide, maybe I will show it to you. For example, here if I draw spacer here, which is basically silicon dioxide, though it will be converging the electric flux, it will add to the capacitance. Moreover, there will be a gate to drain capacitance, there will be capacitance, source to gate. and these capacitances add to the transient response, and therefore the transient response becomes worse and worse as you have these non-planar structures into consideration. Further, when you increase these materials like titanium oxide or hafnium oxide, you tend to though increase the current, you tend to also increase the capacitive loading of the device, right. So, these are the few things which you should keep in mind while designing the geometry. So, with this, let me come to the end of this discussion, and what we have learned is in at least in this lecture is given you a brief idea about design. We have also understood the dependency of threshold voltage on T-fin and H-fin, and we have looked into other design configuration. This one is one of them, which is basically a triangular fin which you can see. You can also have an omega FinFET, where the if omega FinFET is something like this, that if you have a channel here, if you have a channel from here, then it looks like this. So, it's quasi gate all around. So, it's just 3 side and the 2 below are being implemented, right. And depending on the shape of the source and fin, the source to drain resistance actually varies, right. So, if you make it very tapered or very small, you end up having a high resistance, low current, but if you make it wide at the cost of area, you increase the current, right. And these are the few things which you should be aware of as far as this designing is concerned. When we meet next time, we will take care of high frequency modeling and small signal modeling of FinFETs. Thank you.